On the night of March 1st, 1943, a Royal Air Force Liberator bomber was patrolling the Bay of Biscay when its radar operator detected a contact at 8 miles distance. The screen showed a small but definite echo, unmistakably a U-boat running on the surface in darkness that had previously guaranteed invisibility. The pilot turned toward the contact, descended to attack altitude, and approached at full throttle. The U-boat's lookouts, trained to watch for aircraft in daylight and to listen for engines at night, detected nothing until the Liberator was directly overhead. The aircraft released 4 depth charges that straddled the submarine, causing massive damage that forced it to the surface. The crew abandoned ship as the U-boat sank stern first into the Atlantic. The entire engagement lasted less than 3 minutes, from initial detection to final destruction. 6 weeks earlier, this attack would have been impossible. The technology that made it possible was a device the size of a fist, a cavity magnetron that generated radar waves at 10 centimeters wavelength, and it was about to transform the Battle of the Atlantic more decisively than any weapon or tactic deployed in the previous 4 years of war. The story of 10-centimeter radar begins not with military requirements, but with fundamental physics and the limitations of existing technology. Radar had been operational since the late 1930s, employed by the British for air defense and by navies for surface ship detection. But early radar systems operated at wavelengths measured in meters, requiring massive antennas and generating relatively crude images that could detect large targets like ships and aircraft, but struggled with smaller objects. A submarine's conning tower, barely 6 feet wide and perhaps 8 feet tall when surfaced, was at the edge of what meter-wavelength radar could resolve. In darkness or poor visibility, U-boats could operate on the surface with reasonable confidence that radar would not betray their presence. The physics of radar resolution dictated that shorter wavelengths would provide better target discrimination, but generating high power at short wavelengths required technology that did not exist in the 1930s. Conventional vacuum tubes could produce radio frequency energy at meter wavelengths, but as wavelength decreased, power output fell catastrophically. What was needed was an entirely new approach to generating radio frequency power, something that could produce kilowatts of output at centimeter wavelengths in a package small enough to fit aboard aircraft. The solution, when it came, was the cavity magnetron, a device whose elegance and effectiveness would revolutionize not just radar, but the entire field of microwave engineering. The cavity magnetron was invented in February 1940 by British physicists John Randall and Harry Boot at the University of Birmingham, working under the direction of Sir John Cockcroft at the Telecommunications Research Establishment. The device used magnetic fields to force electrons into circular paths inside a resonant cavity, generating microwave radiation at wavelengths determined by the cavity's physical dimensions. A magnetron designed with cavities spaced to resonate at 10 centimeters would produce radar pulses at that wavelength with power levels measured in kilowatts rather than watts. The first prototype, tested in February 1940, produced 400 watts at 10 centimeters. Within weeks, improved designs were generating kilowatts. By summer, production models were delivering 10 kilowatts continuously, enough power for radar sets that could detect submarines at ranges that made interception inevitable. The strategic implications of centimetric radar were recognized immediately by those who understood both the technology and the tactical situation. Britain in 1940 was losing the Battle of the Atlantic. U-boats were sinking merchant ships faster than replacements could be built, threatening the supply lines that kept Britain fed and armed. The submarines operated primarily on the surface at night, using their surface speed to position for attacks and their diving capability only to evade when threatened. If aircraft could detect surfaced U-boats reliably at night, the submarine's operational freedom would be destroyed. They would be forced to remain submerged, reducing their speed, limiting their range, and making them vulnerable to the convoy escort's ASDIC detection. Centimetric radar offered the possibility of winning the Atlantic battle, not through incremental improvements, but through fundamental transformation of the tactical equation. The development of operational radar sets from laboratory prototypes required engineering effort that matched the scientific achievement of the magnetron itself. The cavity magnetron had to be packaged with transmitters, receivers, display systems, and antennas small enough to fit aboard patrol aircraft, robust enough to survive combat operations, and simple enough that operators with minimal training could use them effectively. British engineers worked with American manufacturers. The radiation laboratory at MIT became the center for radar development after the technology was shared with the United States in 1940 to create production models that could be deployed in quantity. By early 1943, centimetric radar sets designated ASV Mark III were entering service aboard RAF Coastal Command aircraft. The transformation from prototype to operational deployment took nearly 3 years, a period that seems glacially slow in retrospect but was extraordinarily rapid by peacetime standards. Every month of delay meant merchant ships sunk, sailors drowned, supplies lost. The engineers and scientists working on centimetric radar understood the stakes with clarity that comes from fighting a war of national survival. They worked through problems of antenna design, receiver sensitivity, display presentation, and integration with aircraft systems under time pressure that allowed no luxury of perfection. The radar sets that entered service in early 1943 were not optimal solutions to every technical challenge, but they were good enough to work, and good enough was all that victory required. The operational advantages of 10-centimeter radar over previous systems were overwhelming and immediate. The shorter wavelength allowed antennas to be smaller while maintaining directional precision, meaning that aircraft radar could scan ahead accurately rather than broadcasting in all directions. The improved resolution meant that a submarine's conning tower, which had been barely detectable on meter-wavelength radar, appeared as a distinct echo on centimetric systems. The increased power meant detection ranges of 8 to 12 miles under good conditions, giving aircraft time to position for attacks before U-boats could dive to safety. Most critically, the shorter wavelength meant that German submarine radar detectors, designed to warn of meter-wavelength emissions, provided no warning of centimetric radar until it was too late. The German Metox radar detector, which had given U-boats warning of approaching aircraft throughout 1942, was designed to receive signals in the meter-wavelength band, where British ASV Mark II radar operated. When centimetric radar was deployed, Metox receivers remained silent, even as aircraft approached within attacking distance. U-boat commanders, trusting their detection equipment, believed they were safe when in fact they were being tracked continuously. The first several U-boats destroyed by aircraft using centimetric radar were sunk without their crews understanding what had betrayed them. The lookouts reported no aircraft sighting before the attack, the radar detector gave no warning, and the survivors, when interrogated, could offer no explanation for how they had been found in darkness on an empty ocean. The tactical impact became apparent in March 1943, when U-boat losses began to spike without corresponding increases in convoy escort strength or changes in tactics. Dönitz, monitoring loss reports, noticed that submarines were being caught on the surface at night with increasing frequency, particularly in the Bay of Biscay, where they transited between French bases and Atlantic patrol areas. The pattern suggested some new detection capability, but German intelligence could not initially determine what had changed. Captured radar equipment from downed aircraft was analyzed, revealing the cavity magnetron and confirming that the Allies had achieved a breakthrough in microwave technology. By the time German scientists understood what they faced, the strategic situation had already shifted decisively. May 1943 became the turning point, the month when U-boat losses reached levels that were simply unsustainable. 41 submarines were sunk that month, representing nearly a quarter of the operational force. Aircraft attacks accounted for many of these losses, with centimetric radar enabling night attacks that would have been impossible weeks earlier. The Bay of Biscay, which submarines had to cross to reach Atlantic hunting grounds, became a death trap where aircraft patrolled continuously and U-boats were detected and attacked repeatedly. Dönitz, confronted with losses that would destroy the U-boat force within months if they continued, ordered withdrawal from the North Atlantic convoy routes. The order acknowledged that Germany had lost the technological advantage and could no longer contest Allied shipping with acceptable costs. The experience of U-boat crews during this transition was terror, compounded by incomprehension. Submariners who had operated successfully for years suddenly found themselves under attack without warning. Aircraft that should have been detectable miles away appeared overhead before lookouts could spot them. Crash dives that had previously saved boats from air attack now came too late, with depth charges falling while submarines were still on the surface. The psychological impact was devastating. Crews that had volunteered for submarine service, accepting known risks, now faced dangers that seemed arbitrary and inescapable. Morale collapsed as survivors from sunken boats spread stories of sudden attacks that gave no chance of defense. The British and American response to their technological advantage was systematic exploitation rather than mere celebration. Coastal Command reorganized patrol patterns to maximize coverage of submarine transit areas, knowing that centimetric radar made continuous surveillance effective for the first time. Aircraft were equipped with improved weapons, acoustic homing torpedoes, larger depth charges with more reliable fuses that increased the probability of destroying a detected U-boat. Tactics evolved to capitalize on the submarine's force response, knowing that boats ordered to remain submerged would be slower, more constrained, and more vulnerable to convoy escorts. The radar breakthrough enabled a comprehensive transformation of anti-submarine warfare that went far beyond simple detection. The German attempts to counter centimetric radar demonstrated both the capabilities and limitations of wartime technology adaptation. By late 1943, German submarines were equipped with Naxos radar detectors that could detect centimetric wavelengths, though only at shorter ranges than Metox had provided for meter-wavelength detection. The warning time was reduced from minutes to seconds, often too little to dive before aircraft arrived overhead. U-boats were also equipped with increased anti-aircraft armament, instructed to fight on the surface rather than dive when attacked, gambling that concentrated gunfire could drive off or destroy attacking aircraft. The tactic occasionally worked, but more often resulted in submarine losses with heavy aircrew casualties as well. The Schnorkel, deployed in 1944, represented a more fundamental response to the radar threat. By allowing submarines to remain at periscope depth while running diesel engines, the Schnorkel reduced the time submarines spent fully surfaced and vulnerable to radar detection. But Schnorkel operations came with severe penalties in speed, endurance, and crew comfort. The U-boat force adapted to survive, but could not recover the offensive capability it had possessed when surface operations were safe. The radar war had fundamentally altered the tactical balance in ways that no countermeasure could reverse. The scientific and engineering legacy of the cavity magnetron extended far beyond military applications. The device that had been invented to detect submarines became the foundation for an entire industry of microwave technology. Radar systems proliferated after the war, used for air traffic control, weather observation, marine navigation, and countless other civilian applications. The magnetron itself found a new role as the heart of microwave ovens, generating the electromagnetic radiation that heats food through a mechanism that is fundamentally the same as the radar emissions that had detected U-boats. The technology developed under the pressure of wartime necessity became ubiquitous in peacetime, its military origins largely forgotten. The human cost of the radar war was measured in submarines that never returned, and aircraft that were shot down attempting attacks that earlier technology would not have enabled. The 41 U-boats lost in May 1943 represented over 2,000 German sailors killed or captured, young men who had volunteered for submarine service, and who died because their equipment could not detect the threat hunting them. The aircraft losses during the same period represented hundreds of Allied aircrew, shot down by anti-aircraft fire or lost to mechanical failures during long overwater patrols. Technology killed efficiently and without discrimination, claiming victims from both sides in a contest where advantage shifted based on engineering capabilities rather than courage or skill. The recognition that radar had been decisive in the Battle of the Atlantic came gradually, obscured during the war by security requirements that kept magnetron technology classified and revealed only slowly in the decades after. The public narrative of the Atlantic battle emphasized convoy tactics, escort vessel numbers, and the closing of the mid-Atlantic air gap. These factors were important, but they were enabled by the technological foundation that centimetric radar provided. Without the ability to detect surface U-boats at night, aircraft patrols would have been ineffective regardless of numbers. Without forcing submarines to remain submerged, convoy escorts would have struggled to engage targets that could outrun them on the surface. The radar breakthrough was the linchpin that made other improvements effective. The comparison between the impact of radar and the impact of ultra-intelligence reveals different mechanisms of advantage. Ultra, the British code-breaking operation that read German naval communications, provided strategic warning of where U-boats were concentrating and allowed convoy routing to avoid wolf packs. This was invaluable for preventing attacks, but did not directly enable the destruction of submarines. Radar provided tactical capability, allowing aircraft and escorts to detect and attack U-boats that would otherwise have remained invisible. Ultra told the Allies where to look. Radar allowed them to see what they were looking for. Both were essential, and neither alone would have been sufficient. The lasting tactical lesson from the radar war was that technological surprise could be decisive, but that the window of advantage was temporary. The magnetron gave the Allies complete tactical superiority for perhaps 6 months, from its initial deployment in early 1943 until German countermeasures began to appear in late summer. During that window, U-boat losses spiked and the strategic balance shifted, but by 1944, the advantage had eroded as German submarines adapted with snorkels, improved radar detectors, and modified tactics. The fundamental transformation remained. Submarines could no longer operate freely on the surface, but the absolute dominance of the initial surprise had passed. Technological advantages were real but transient, requiring continuous innovation to maintain. The engineering achievement represented by operational centimetric radar should not be understated. The magnetron itself was a triumph of physics and materials science, but translating that laboratory device into a system that could be manufactured in quantity, installed in aircraft under field conditions, operated by crews with minimal training, and maintained under combat stress represented engineering challenges as difficult as the original invention. Thousands of engineers and technicians contributed to solving problems of power supply, cooling systems, antenna design, receiver sensitivity, display presentation, and integration with aircraft electrical systems. Their work, largely anonymous and conducted under security restrictions that prevented public recognition, was as essential to victory as the invention itself. The post-war development of radar technology followed trajectories established during the wartime crash programs. Wavelengths continued to decrease, moving from 10 centimeters to 3 centimeters and eventually to millimeters, each reduction providing improved resolution and discrimination. Power levels increased through improved magnetron designs and eventually through entirely new technologies like traveling wave tubes and clystrons. Processing of radar returns evolved from simple analog displays to digital systems that could track multiple targets, distinguish between types of objects, and integrate with weapons systems. The World War II radar sets that had revolutionized anti-submarine warfare became primitive antiques within a decade, superseded by systems that their designers would have considered science fiction. The memorial to the scientists and engineers who developed centimetric radar is scattered across museums and technical histories, preserved in devices that most visitors do not understand and cannot appreciate without context. The cavity magnetron that changed the war looks unimpressive, a metal cylinder with no moving parts and no obvious connection to the dramatic events it enabled. But that cylinder represented a breakthrough as significant as any weapon developed during World War II, a technology that transformed impossible tactical problems into solvable challenges, that shifted strategic balance not through incremental improvements, but through revolutionary capability. The men who developed it, working under time pressure and resource constraints that would cripple most modern projects, achieved something that military forces have been chasing ever since: a decisive technological advantage that changes the nature of warfare itself. The irony of the radar war was that neither side could maintain permanent advantage. Every innovation was eventually countered, every tactical surprise eventually anticipated, every technological breakthrough eventually matched or neutralized. The cavity magnetron gave the Allies dominance for months, but German responses eroded that dominance even if they could not eliminate it. The competition continued through the war's end and beyond, with each generation of radar matched by each generation of countermeasures, the cycle repeating in the peculiar rhythm of technological competition, where advantage alternates between offense and defense, detection and stealth, innovation and response. The U-boats that survived the war and were captured by Allied navies were studied intensively, their late-war modifications documented and analyzed. The Type 21 submarines, designed for extended underwater operations and equipped with snorkels and improved batteries, represented Germany's adaptation to the radar threat. These boats demonstrated that submarines could remain effective even after losing surface freedom of movement, provided they were designed from the beginning for underwater operation rather than adapted from surface designs. The principles established by these late-war boats would guide submarine development for the next generation, leading eventually to nuclear-powered submarines that never needed to surface at all. March 1943 to May 1943. 3 months that transformed the Battle of the Atlantic from a grinding stalemate into an Allied victory that was decisive, if not yet final. The transformation was enabled by a device the size of a fist, producing radar waves at 10 centimeters wavelength, generating echoes that revealed surface submarines with a clarity that previous technology could not achieve. 41 U-boats sunk in May alone, hundreds more lost over subsequent months, a submarine force that withdrew from the North Atlantic acknowledging defeat that was technological as much as tactical. The radar war was won not through courage or numbers, but through engineering, through the application of physics and material science to military problems, through the transformation of laboratory experiments into operational weapons that killed efficiently and decided battles that determined the course of the war. 10 centimeters changed everything overnight, and nothing in submarine warfare would ever be the same.